Herkese merhaba tekrardan. Öncelikle hepiniz hoş geldiniz. Bugünkü webinarımıza katıldığınız için teşekkür ederiz. Ben Ali Fırat Bucak. 5 yıldır yaklaşık BİAS Mühendislik'te çalışıyorum. Görevim titreşim akustik takım liderliği. Bugün sizlere distribütörü olduğumuz Dytran firmasından bir konuğumuzla birlikte piezoelektrik sensör teknolojisiyle alakalı bir webinar gerçekleştireceğiz. Bu webinarda ben moderatörlük yapacağım. Webinar dilimiz de İngilizce olacak. Bu webinar süresi boyunca sorularınız olursa chat'e yazabilirsiniz. E, bu webinarın sonunda soru cevap e, kısmında biz bu soruları da cevaplayacağız size. E, Şimdi sözü Kevin'a devredeceğim. Bu arada Kevin bu sabah geçirdiği bir medikal rahatsızlık nedeniyle ağzında bir medikal rahatsızlığı olmuş. Sağlıkla alakalı bir problem varmış. Biraz yavaş ve tane tane konuşmaya çalışacak. E, Bu konuda da bilgilendirmek istedim. Thank you all for joining us today. I would now like to hand over the microphone to Kevin Mestora, the sales director of Dytran. He will guide us through today's presentation. And if you have any questions, feel free to write them in the chat box, and we will answer them during the QA session and at the end. Kevin, you can begin with introduction and begin with your presentation whenever you're ready. Thank you. Kevin, we cannot hear you. I think your microphone is closed. Yeah.
Hello, thank you, Ali. Hello, everybody, and good afternoon. Very happy to be a part of this presentation. Thank you for the invite. We're very excited to have BİAS representing our sensors, Dytran sensors, in the country of Turkey, and so we appreciate them putting this together. I'm going to go ahead and turn off my camera. Just wanted to say hi to everybody, and I will share my screen. And we will start talking about piezoelectric accelerometers. And if anybody has a question, just feel free and jump in. So today, hopefully this works. There we go. Today we're going to talk about piezoelectric accelerometers and piezoelectric sensors. I also like to compare and contrast DC MEMS accelerometers because that's becoming a much larger part of our portfolio. And it's a great option for many testing applications, but it's also not the answer for every application. So I like to do some comparing and contrasting between the two technologies. So Dytran, we're a maker of advanced sensors for a dynamic world. And so let's just jump in. A couple little things about Dytran before we start talking about the technical things. Dytran is very much an aerospace company. We are ISO 9001 and AS 9100. In addition, we also have ISO 17025 accreditation, so every sensor that we ship is shipped with an accredited calibration certificate. We do a lot with aerospace and space. If you saw the successful launch last night of the SpaceX Starship, there was a lot of Dytran sensors on that launch. So a little bit about Dytran. We are located in Los Angeles, California. We have been around in business now for 43 years. We started in 1980 in Buffalo, New York, and then we moved to California. Our founder, Nick Change, started his career at Kistler Instruments in Buffalo in 1958, and then he moved over to PCB in 1968 as president, and then he started Dytran in 1980. So we have a long history in this sensor industry of making accelerometers and piezoelectric sensors. We have about 40,000 square feet at our factory, and it's growing. We plan on expanding that facility over the next couple years. These are the topics that we're going to go through today. I won't go through this list right now. We're just going to jump right in because we're talking about piezoelectric technology to measure force, pressure, shock, and acceleration. So, as I mentioned, our founder started his career in the 1950s, and so it's been around for over 80 years, and yet we still make 80 new products a year from this amazing piezoelectric technology. And the reason, after 80 years of developing sensors, that we still can make so many new types of sensors is because of all of this capability. Ultra small size. We make the world's smallest accelerometer, 0.2 grams. We make IEPE sensors out of these with this technology, or if you're familiar with ICP, but it's the ability to have a two-wire system instead of like a strain gauge or voltage sensor that has 4 wires. Our sensors only require 2 wires. We can offer a wide dynamic range anywhere from 0.1 G all the way up to 100,000 G for shock. We offer wide temperature ranges. The SpaceX launch last night had sensors on it that are rated to minus 320 F, and we also make sensors that are rated to plus 1200 F. So this same technology can go minus 300 to plus 1200. It's quite amazing. We do offer at Dytran a lot of DC MEMS variable capacitance sensors, and they are the lowest noise sensors on the market. But if you compared a DC MEMS sensor to a piezoelectric sensor, you would see an exponential level difference of noise on a piezoelectric sensor. Piezoelectric sensors have amazing low noise floors. Most of our sensors that we sell in the piezoelectric industry are 10 millivolt per G, 500 G sensors. And even though there's not that many applications that generate 500 Gs, you can actually resolve milli-Gs with a 500 G sensor, so you can use the same sensor in multiple applications. That's not the same case with DC MEMS sensors. If you have a 10G application, you must get a 30G or 20G or 10G sensor for that application. You cannot get a 500G because the noise is too high. We make sensors with broad frequency range, anywhere from 0.1 hertz all the way up to 20 kilohertz. And today, almost every data acquisition system offers IEPE or charge mode conditioning for your accelerometers. As far as applications for these sensors, I won't go through all this. For the most part at Dytran, anybody that's making a product and has to test it uses our type of sensors. So that's a lot of automotive, aerospace, space, and then at the end of the day, a lot of shakers. So a lot of products get tested on shakers, whether it's a car muffler or a laptop or a cell phone, whatever it is, that's the application that we get involved with typically. Okay, so when you are searching for a sensor or you've purchased a sensor, these 3 documents are very important. And you can typically find these the first two documents on our website. And I will say I apologize for the condition of our website currently. It is not acceptable. It was taken down a couple months ago, and we've had to rebuild it. And today, all the data sheets are on there, but the functionality is still lacking. And we're working on updating it. So I just wanted to say I apologize for the condition of our current website. We are working on it, but you can now find these on the website. So the first one is up in the upper right, called an outline installation drawing. It's what we call the 127 drawing of the sensor, and it has the dimensions of that particular sensor. It also includes any mounting conditions that would be included for that sensor, maybe the recommended torque, if it's stud mounted, and the surface finish preparation, if you're going to glue mount it or stud mount it, either one. So a very important document called the outline installation drawing. In the middle here is our data sheet or specification sheet. So all of the pertinent information of your sensor is listed here, from the weight to the sensitivity to the G range to the frequency to the noise, temperature, whether it's isolated or not, whether it has a connector, how to mount it, etc. And then there are three typical plots of data that we provide you. The first one here is the low end roll off, the AC coupling of that sensor. The other is the typical temperature deviation. And then the last one is typical phase of a particular accelerometer. So very important data sheet that you can find on the website. And then the last piece of documentation here is the calibration certificate. You'll notice in the top right, it says A2LA. Again, we're accredited from 17025, so every sensor comes with this certificate. We give you 10 points of data. We start at 20 hertz and go up to the full scale frequency of the sensor, typically 10 kilohertz. And then we plot those data points here to give you a typical frequency response curve. There are two things I wanted to highlight here. One, the reference sensitivity of an accelerometer is the 100 hertz data point of the accelerometer. So that's what you would see on your calibration sticker. That's what you would use to enter into your data acquisition system as you set it up. And then the other piece of information I wanted to highlight is that we have the capability of going down to 1 hertz and the ability to go up to 17 kilohertz. But we're accredited through ISO from 1 hertz to 10 kilohertz. Okay. So today we're predominantly talking about using piezoelectric technology to measure vibration and shock, but you can also use the same technology to measure pressure and force. Okay, I want to talk a little bit about the difference between dynamic and static measurements. Typically, you would use a piezoelectric accelerometer for a dynamic measurement that involves shock and vibration. This means that the physical quantity that you're trying to measure, whether it's pressure, force, or acceleration, is changing rapidly, let's say over 500 hertz. And a static measurement would mean that it's the physical measurement you're trying to measure is changing slowly over time, let's say under 500 hertz. And this is where you would use a DC MEMS variable capacitance accelerometer. Typical examples of a dynamic measurement would be NVH automotive testing, modal testing, electrodynamic shaker testing, things like that, anything that has high frequency. Examples of a static measurement would be like your bathroom scale or acceleration due to gravity, things like that. And as an example, if I had a test that was 100 Gs at 100 Hertz at room temperature and size didn't matter, which of these two sensors would I use? And the answer is either one of those sensors would work perfectly in that application. What usually determines what sensor you use could be your data acquisition system that you have and what it's set up to do, or it could be the legacy of the test. What have you used before in that test? Or it could just be pricing and delivery. So there are times when you can use either sensor technology for the same application. And the reason that we put the bathroom scale on here is because that's a perfect example of a transducer. A transducer is a sensor that takes one form of energy and converts it into another form of energy. So your bathroom scale takes your mass, your weight, and converts it into an electrical readout. Our accelerometers take vibration and shock and convert it into an electrical readout. So we make accelerometers, we make sensors, and we make transducers. So now that we know what a transducer is, let's talk a little bit about what is piezoelectric technology. So piezoelectricity is the ability of some material like a crystal or a ceramic to generate an electrical output, an electrical potential in response to an applied mechanical stress. It comes from the Greek word piezo, which means to squeeze or to press. I like to say that it means to change. So there's also a technology out there called piezo-resistive, a strain gauge. And we're all typically familiar with strain gauge technology. And piezo-resistive means changing the resistance in the wire to get a linear output to measure force or torque or pressure. In this industry, we're squeezing this crystal to get an electrical output. So think of it like a sponge. If you see this crystal down here, if I squeeze that crystal, I get an electrical output measured in coulombs, and the size of that charge is so small that we measure it in picocoulombs, very, very small amount of charge, but it's extremely linear. So if I squeeze a little, I get a little out. If I squeeze a lot, I get a lot out. And we use a lot of different materials at Dytran, depending on the application and the temperature that you need. So most of our sensors are either quartz or ceramic, but we also use GaPO4. We just actually purchased a company in Austria. Right now, we're in the process of doing so. And this is an amazing material that will allow us to offer accelerometers at 800C for turbine engines, exhaust manifold testing, hypersonic testing, things like that. Accelerometers come in all shapes and sizes. That's why I like to show this screen here. The one in the middle is our world's smallest accelerometer. That's a 0.2 grams accelerometer. And then right above it is the world's smallest triax. Over here on the left side is what we call the grenade. It's a massive accelerometer the size of a Coke can, and it's used to measure earthquakes. And then you can see these square accelerometers. These are the DC MEMS accelerometers that we offer. Okay. Now that we know what a piezoelectric technology is and a transducer is, let's put them together and make a sensor. So there are two types of piezoelectric sensors. There's voltage mode and charge mode. So if I put this crystal in this accelerometer right here with no amplifier, no wires, no nothing, not no wires, but no amplifier, I will get an output. It's called self-generating. If I shake this accelerometer with that crystal in it, I will get an output. But the output, as I said, is in picocoulombs. And it's very difficult to measure picocoulombs. So you have to convert the picocoulombs to voltage either in a charge amplifier or in your data acquisition system or in the sensor. If you do it inside the sensor, then we call it a voltage mode accelerometer. And that amplifier that's inside the accelerometer has a name. I don't know why in our industry they name this amplifier, but they do. Every manufacturer in the world has a name for it. So IEPE, ICP, Piezotron, Isotron, CCLD, LIVM. Whoops. You'll hear lots of different names, but it means exactly the same thing. So if you had a sensor from Endevco or PCB or Dytran or B&K or Kistler, it does not matter. It is the exact same input and the exact same output, which makes them very easy to interchange on your data acquisition system. Okay. This is what's inside of an accelerometer. We make both compression mode and shear mode designs. Today, 90% of all of our accelerometers are shear mode. We still do offer the compression mode design because it's very robust. We use these for industrial applications and for shock applications. You can see they both have the same similar material. Hopefully you can see my mouse moving around. But on the bottom of the sensor is the base. And at Dytran, we use titanium for our base in most of our sensors. Some of them do have other materials, whether it's stainless steel or Hastelloy, but most of them are titanium for strength to weight ratio. And then we have the crystal stack. So here's the crystal. We have 4 crystals here being summed in this particular design. This big green thing on top is a seismic mass made out of tungsten. And then we assemble the whole system together with this preload screw. And so that's a compression design. What's not being shown here is the IEPE amplifier. Okay. On the shear mode accelerometer, it's the same concept. We have the base, and then we have the crystal here, and the seismic mass here, and the preload screw here. But the difference being we have polarized the crystal to only give an output in shear mode. So when it goes up and down in the Z direction is when you get an output, okay? Not in this direction. So that's what makes it unique. And the crystals, these are the crystals. Once we cut them and we polarize them, this is what they look like. There's lots of different designs and shapes that we utilize at Dytran. This is a cartoonish depiction of what a shear mode IEPE accelerometer looks like. So you'll see on the left side, we have 2 crystals with an insulator in between. And the crystals are aligned polarity so that they are neutral, sitting at rest. And then as we start to accelerate, we start to align the polarity. So plus is in the up direction and negative is in the down direction. and we get a deformation that we're shearing the face of this crystal. This deformation that you see here is cartoonish because the actual deformation is in the angstroms. The human eye cannot see it. Okay. So when we're using a voltage mode, IEPE or ICP accelerometer, we can use either quartz or ceramic material. Quartz is typically used for NVH applications in automotive. It's used for higher frequencies and it's used for higher temperatures. Ceramic is used for more modal testing and seismic applications. It's very low noise, very, very stable, very high sensitivity, but it's also very thermally unstable. So depending on the application, we will choose either quartz or ceramic. So a voltage mode transducer has built-in amplifier, as we said. It's stable from about minus 40 C to 160 C. If you go above that, you would then need to go to a charge mode sensor. In my opinion, the only reason you would ever use a charge mode accelerometer is temperature. If you're above 160 degrees C, you would need a charge mode accelerometer. With voltage mode sensors, you can also integrate it with TEDS. TEDS, I have a slide on that coming up, stands for Transducer Electronic Data Sheet. And we put an EEPROM chip in the sensor, and we put the calibration information on that chip so that if your sensor has TEDS, it will automatically calibrate. This is a very important slide. IEPE sensors, the amplifier inside of accelerometers, means constant current. So that's what it means. It means that your sensor needs anywhere from 2 to 20 milliamp constant current. Most data acquisition systems provide 4 milliamps, which is adequate. And it does require a voltage of 18 to 24 volts DC. So again, the takeaway here is it requires constant current. IEPE means constant current. If you use standard DC power, 24 volt power, with an accelerometer, you will destroy it. The output is proportional to the acceleration, so you get plus minus 5 volts out. So if you have a 10 millivolt per G accelerometer, it is a 500 G accelerometer. 10 times 5, you get 5 volts at 500 Gs, etc. And because IEPE is a 2-wire device, it makes it very easy to use, and we can use coaxial cables where the signal rides on a single axis accelerometer. The signal rides on one wire and the power and ground ride on the other wire. Very unique in the industry. Okay, let's talk a little bit about frequency response. Let's go back to this slide, and you'll see this little tiny sensor here for the upper frequency. This sensor has almost no seismic mass, and so the natural frequency of that accelerometer is about 100 kilohertz, which means I can use it out to 20 kilohertz. Where this seismic accelerometer on the far left, excuse me, has a natural frequency of 2 kilohertz and a usable frequency of about 500 hertz. So the upper level frequency of an accelerometer is limited by the design of the sensor, the mass the connector, the cable, etc., determines the upper frequency limitation. The low end frequency is determined by what we call the discharge time constant. It is set at the factory. It cannot be changed. We do list it on the data sheet what your DTC level is, but it's much easier to determine what your low end frequency is on the data sheet by just looking at the frequency response of the data sheet. It'll give you the low end frequency and the upper frequency. Typically, it's going to be somewhere around 1 or 2 hertz. Okay. And I have a graph to show you what that looks like here in a second. Right here. So this is a typical output of a piezoelectric accelerometer. So in the middle here is where we want the output to be set between 0.2 and 0.3% of natural frequency. And then we want to understand the roll-off at the low end, and we want to understand where the first mode of the natural frequency of that accelerometer is. We want to make our output as linear as possible. And as I said, we want to then understand the low end roll off, which you can see down here, starts to roll off at 5% at about 8 hertz. And then we show you the 10%, the 15%, the 3 dB, and then what we call the 6 dB corner frequency. Now, typically, an accelerometer would be around, as I said, 1 or 2 hertz at 5% or even 15 or 10%. So this sensor has very high low frequency. Ours, typically, it would be way down here. On the left here is a typical schematic of an IEPE amplifier. So ICP, CCLD, isotron, piezotron. This is exactly the same thing. They all mean the same thing. This is the schematic for that. And it hasn't changed since 1978. I'm going to skip this slide because there's way too much words, and I'm going to go right to a video and show you a video. So I want to talk a little bit right now about triboelectric noise. Triboelectric noise is noise from your sensor cable, not the sensor itself, but the cable. And this demonstration has a charge mode accelerometer with an IEPE cable. So it's important to know that each sensor, voltage mode and charge mode, require specific cables. If you have an IEPE sensor, you need an IEPE cable. If you have a charge mode sensor, you need a charge mode cable. And this is what happens if you don't do that. This is a charge mode accelerometer with an IEPE cable. We're not going to move the accelerometer. We're just going to shake the cable. And here we go. And look at the noise that we're generating from just shaking the cable. Okay. So what's happening is dissimilar material are rubbing against each other, building up spurious charge, and it's discharging into your data acquisition system. And so two things are wrong here. One, you're using the wrong cable, and number two, you're whipping the cable. You need to tie your cable down on your test article. So if I replace the cable with a proper cable and I whip it, you'll see that a lot of that noise has gone away because these low noise charge mode cables dissipate that spurious charge. But you can still see some perturbations here where we're whipping and shaking the cable. So don't do that. So the takeaway here is use the right cable with the right sensor, use and tie your cable down off of your test article. Okay. All right, a couple do's and don'ts. If you look at a data sheet of an accelerometer, you'll see that it says the measurement range is whatever that sensor is, 500 Gs, 100 Gs, whatever it might be. But right below that, it says safe shock or safe overload, 5,000 Gs. And that's so that you can drop your accelerometer from a couple feet on your desk, or you can drop it on carpet. But if you drop your accelerometer from 5 feet onto a concrete floor, you will break the accelerometer. So don't drop them. Don't hold them from the cable. Make sure you use a proper power supply. Do not remove your sensor with a hammer. Do not use uncalibrated accelerometers. We recommend that you calibrate once a year. If you do not calibrate locally, we'd be happy to do that for you. And it's always important to understand that these are electrostatic sensitive devices. We ship them in electrostatic protected bags, but it's always important not to touch the pin of the connector unless you're grounded. Okay, so that's always a good reminder. All right. I mentioned TEDS earlier. This is what the TEDS chip stores inside the accelerometer. So if you're interested in learning more about that, we'd be happy to share more information for you. So let's now talk a little bit about mounting our accelerometers. There are 3 ways to mount an accelerometer. You can stud mount it, you can glue it, or you can use a magnet. We do have some customers that like to use magnets. We offer many different types of magnets at Dytran. Most people either stud mount it or glue it, but in some applications, you are not able to drill and tap into your test article. If you're trying to test a cell phone, you're not going to drill and tap and mount an accelerometer. You're going to glue it. Excuse me. So from these 3 ways of mounting an accelerometer, they each have their own benefit and also their own issues. If you want to get the highest natural frequency of an accelerometer, then you would stud mount that accelerometer, and that can get you almost out past 10 kilohertz. If you're gluing the accelerometer, it's important to understand that the glue, the adhesive that you're using, is introducing a new spring mass system into the measurement. And this perturbation that you see here can occur anywhere along the measurement frequency, depending on how well or poorly you mount the accelerometer. If you care about high frequency, then you need to use as little material as possible to make a secure adhesion. If you're trying to get 10 kilohertz, it's very important how you mount the sensor. If all you care about is 1,000 hertz, then it's less critical, okay? Some of this is redundant. When you're mounting an accelerometer, some of the sensors are glue mounted, some of them have stud mounts. Some stud mount sensors have a female thread where you use an external thread stud. Some of them have an integral stud. In both of these sensors, you have to pay attention to where the orientation of the connector ends up. There's many ways to help do that. You can use shims, or we also make an amazing mounting adapter called Romo that allows you to orient your sensor exactly the way you want it to orient and then tighten it down. And I think I might have a picture of that. Some of this is redundant. I'm going to skip some of it. This is a good slide right here, talking about mounting your accelerometer and surface preparation. Before mounting the accelerometer, we want to make sure that we clean the mounting area thoroughly with compressed air, remove all contaminants. We then want to use a light coating of silicone grease on the mating surface, and this allows you to lubricate the surface and ensure that you have perfect uh, uh, intimate contact between the sensor and the mounting surface to maximize high frequency transmissibility for the accelerometer. The other thing this picture is showing is tying your cable down properly off your test article so that the cable does not whip. Some of this is redundant. As we said, do not use a hammer to remove your accelerometers. Now, even though there's only 3 ways to mount an accelerometer, that ignores the fact that many customers use a base. Whether they're going to glue it or whether they're going to stud mount it, they would rather use a base because that's your sacrificial part. It's much cheaper than breaking an accelerometer. If you're going to be putting it on and taking it off quite often, you'll want to use a base. We make hundreds of different bases at Dytran. Okay. Curved mounting. We also use magnets for curved mounting surfaces and things like that. And then the next thing I want to talk about is electrical isolation. Okay. Most accelerometers that we offer, that anybody offers, are not electrically isolated. So it's important to understand if your test requires isolated sensors, check to see if your sensor is isolated or not. If it's not, make sure you isolate somehow, whether it's through a base, whether it's through the adhesive, or whether it's through Kapton tape, whatever you want to use to isolate. So here's a good example. This video, the first accelerometer here is on this energized test article, and it has an accelerometer that's not isolated. And then we're going to move it to the isolated base, and then we're going to move it to the isolated accelerometer. We're going to hit the table with a hammer and see what happens. So we come in, we hit the table, and look at this noise right here. This is all noise. You can barely even see the hammer. Here's the frequency content, the FFT, and it's all 60 hertz noise. So let's move the sensor to the isolated base. And now that noise is gone. And look at the clean data that we're getting on the time domain and the FFT. And then if we move the sensor or the cable to the isolated sensor, we get the same result. So the takeaway here is most sensors are not isolated. Understand if you need isolation, and you can use a base or use an isolated accelerometer to solve your challenge. And then the last thing we want to talk about is mounting frequency. I'm not going to show you the video. It's not very exciting. It's just a guy mounting sensors on the shaker here. So we have a shaker with a back-to-back reference accelerometer with this standard general purpose accelerometer. In the top here, we're going to stud mount it on here. And down here, we're going to glue it with super glue. And you can see the data. So on the top graph, we get really good data out to 10 kilohertz, and then we start to take off with the data, which is good. And down here, when we glue it, he does a really good job of gluing the accelerometer, and he gets about 90 kilohertz of data before we start getting some perturbation from the super glue. But that's really good high frequency data for a glue accelerometer. And then if we go to the next slide, we'll do the same thing with wax. With wax, he gets really good data out to 9 kilohertz. And then if he puts too much wax on, you can see the difference in the data here. He barely gets any good data out past 2 kilohertz. Okay. And then magnets, we typically claim we can get 3 kilohertz with a magnet. Okay. 2 to 3 kilohertz. As far as selecting a transducer, we are working on our website to add a sensor configurator. Hopefully that'll be up there soon. These will be the questions that we ask you when you're selecting a sensor based on your test. We want to know what the maximum space is, what the mass loading implications might be. We want to know what the G levels are, what the frequency levels are, the temperature, the environment. Is it inside or outside? Is it going to have a connector or a cable? Are we going to glue it or stud mount it? All of these pertinent questions can then help us select the proper sensor. This is redundant. I already mentioned it. And some general care. We already talked about that's redundant. Sorry about that. There is some troubleshooting that you can do with accelerometers. You can always check your bias voltage. You should have 11 volts AC. If you do not have 11 volts AC bias, then the amplifier is most likely damaged. If you're having some type of anomaly, I would always recommend changing out your cable first to check to see if it's the cable. If it's not the cable, check your bias. If it's not the bias, make sure it doesn't rattle. And then if it still is having an issue, you can use a handheld shaker to check it. If you do not have one, you can send it to us to do an evaluation. Okay. And I think that's it. So I do appreciate the opportunity to present today and discuss Dytran piezoelectric accelerometers with you. We're very proud to support the country of Turkey with our sensors and our solutions, and we appreciate BİAS and everything they do to support us there. If you have any questions, be happy to take them on the chat, or you can email me. You have my email. I can send this presentation to BİAS, and they can send this to you, to anybody that wants it. Okay?
Thank you, Kevin, for this informative presentation. I hope it was very useful for everyone, and you can write your questions in the chat or just unmute your microphones to ask them. So if you have not any questions, thank you again for joining us, and we will share the recording as soon as possible of this webinar. So see you at the next future events. Thank you for joining.
Thank you, Ali.